Okay. Okay.
Hey guys, we're the Nerd Herd. It's Kimberly again.
Hi, I'm Hope Windle.
Chris Crowe at your service.
And I'm Katie, and I'm super excited to be here.
Okay, so today we're going to learn about two sets and whole numbers and the number theories, enumeration, and computations. So we can classify sets by grouping them and grouping a set in a universe, and we can explain that by using a Venn diagram. Hope's going to show us what a Venn diagram is exactly.
Yeah, thanks, Kimberly. This is what a Venn diagram looks like. And this is going to be everything that's contained and allowed in a universe. The universe is going to be represented by the letter U. And then we have a set that's A. And that's what all these elements, all these letters, this time it's going to be letters. It could be shapes or numbers or colors or any of these things. But right now we're just using letters. And then we're going to have a set B and a set C. And then a Venn diagram is this interlocking of circles, and however many sets you have is how many circles you're going to have. And then where they overlap is going to be where your unions and intersections are. But Chris, what is the difference between a union and an intersection?
I'm glad you asked that, Hope. So the difference between union and intersection is kind of small, to say the least. So when you're thinking of union and intersection, you want to think of them as simpler terms. So union is going to be considered an or term. And what that means is when you're talking about things in union, so let's say you have letters A and B in one circle and then C and D in another circle, and then they have one letter, let's say E, in between for whatever reason. So union is going to be or. So the items or shapes or whatever you choose that are in circle A and circle B, or circle A and B. And then intersection is going to be the and statement. So in this case, letter E in the middle will be the and because it's in both circles A and B.
Okay.
And when it comes to those different unions and intersections, they're going to be in the sets. And what those letters are going to be called are variables, as we're all well aware. Now, Ms. Katie, where exactly do you need to put those variables?
Okay, yeah, I'd love to answer that, Chris. So whenever we have the variables, we see here that in the universe, we have the letters A, B, C, D, E, F, and G. And we see that in A, we have B, C, D, G, and H. Now, before we write anything, let's read all of the different sets, okay? So we have those letters in A. B, we have D, F, G. And then in C, we have D, G, and H. So looking at those numbers, Hope, do you see anything that is like in those in the Venn diagrams A through C?
I see the letters D and H in all three sets.
That's exactly what I saw. So where do you think we could maybe put those?
I think we could put them right in the middle because that's for all the circles overlap. I'm sorry, I'm really new to this technology.
Oh, no, I think you're doing a great job. So putting those in the middle is letting us know that all three of those, A, B, and C, have those in common. So then we see that in A, we should have the things that are left over, because remember, we've already placed D and H in each of those. You see how they all three interlock there. So in A, we should have B, C, and G. But wait, doesn't C have G as well? So where would we put that one? In between A and C, because those show that they share that variable, which will be very useful later on. So the only one that's left is F, and that should go into B. So we see there that in between the C and B, that is the set, and then again between A and B. So I know that you may be thinking, well, what about the letter A? Because it's in the universe, right? Well, it is in the universe, as well as E And so we just put those over to the side outside of the Venn diagram because they're not an A, B, or C. So talking about those things, the different ones that are empty sets and things, Ms. Kim, what is a complementary set?
In set theory, the complementary set is a complement of set A, and it refers to the elements that are not actually in the set A, so everything outside the set A.
Okay.
So we'll write down A, and then it would be E. Okay, so now that we know what complementary sets are, we're going to talk about shapes and colors and different, how we organize those. Do shapes need to be treated differently than numbers? Chris, can you tell us that?
Yes, I can indeed, and yes, they do need to be treated somewhat differently. Not overly differently, but to a certain degree. So when it comes to the shapes you see here in the Venn diagram circle A, we see there are a very specific set of shapes. We have blue and red hexagons as well as circles, and everything else, including the two little triangles at the bottom, as well as the larger triangles, are all outside. Now, when it comes to intersections and unions, shapes can play a different part. They can be combined in certain ways that so far we haven't seen numbers do so, especially when it comes to intersections, because those are what we can, like I said before, they can be considered the combining terms.
Hey, Chris, when I look at that, it's a bit confusing. Is there maybe a way that you could help me explain that would kind of make it easier?
There is an easier way to do that.
I was thinking that maybe I could create a key, and in that key that I could label, because looking at it, and I think that you might agree, that we have, like you said, the circles, the hexagonal shapes, the triangular, and then we see that there's large and small and also blue and red. Is that what you see?
That is exactly what I see. You've stolen the words right from my mouth.
All right. It's like we're on the same team or something here. Team learning. So I see here, I'm still a bit confused. I hope there might be a way that I can help my little confused mind. I think that if I had this paper right in front of me, if I was still confused, maybe look at that top blue circle there. Well, I know that it's large, so I can maybe write an L and then a comma, and then I could write that it's B, so write a B for blue, and I also know that it's a C, a circle. So I could go through on each of those shapes, and I think that that might help me if I was writing it on paper, that I could maybe separate those to help my mind keep it straight.
Okay, well, let's go ahead and fill out these so we can get a better idea whenever we are filling out, like whenever we see, because we learned about unions and intersections. Let's see where C is a union with H. So that would mean like circular shapes, and it would be union with hexagon. So it would be anything that is circular or hexagonal. Whenever we're writing this out in that set. And then this set would be anything that is not a red triangle, and so on and so forth. So, Kimberly, is there a way to write out large hexagons and other groups without using all those words?
So exactly, it's like the opposite of what you just did. So if we had large hexagons, we could just put simply, like it is there in the first one, L union 8, standing for large hexagons. And then like circulars and hexagon, it's just either or. But now that we know how to label them, is there an way to write shapes that are not red triangles here?
Again, like when we just saw this little list here, and this is the way we would write anything that is not a red triangle, because we know earlier, as you explained, the complementaries to something, the complement to a set is anything that's not in that set. So anything that's not in a triangle would be with a little line over it, and it would be where that intersects, because we're going to remember the intersection means to be or. So it's not red and not triangular. That would be the way we wrote that. So we know about sets and all these other different things. So how can we talk about numbers, and when we get into bigger numbers, like how are the place values of different systems factored in when converting into what we normally use? Like, take a look at this, Chris. This is Egyptian hieroglyphs. Could you just explain this to us? Like, what would this symbol be?
Well, I will do the best that I can. I will understand the Egyptian language using my tiny brain. What we see here are the different symbols, the same way that we use numbers. So our numbers can be considered symbols as part of the Indo-Arabic numeral system that we use. And looking at this chart here, we see the Egyptians had their own set of symbols. So we see, going through the graph, we see the single slash, considered a staff symbol, is representing what we know as number 1. What looks like the intersection sign represents the number 10. The question mark looking design in the third one represents the number 100, so on and so forth, going through with the different symbols. And those symbols are representing the place values that we see as the numbers. So when going through letter A, we see the 3 symbols at the beginning represent different numbers, such as 10,000. So the 3 of them, that's going to be 10,000 times 3, which will give us 30,000. And now going through the intersection symbols, we see a total of 5 of them. And again, if we're looking at the graph, we can see that the intersection symbol represents the number 10. So following the same pattern, we can do 5 times 10, giving us 50. And now finally, we see the 4 individual slashes at the very end, which represent the number 1, which leaves us with 1 times 4 equaling 4. And now combining all of those numbers together, we get 30,054.
Thank you, Chris.
You are very welcome.
So,
Katie, can I find the value faster by adding or multiplying?
well, I see here that these are Roman numerals, and I see that, of course, as Christopher showed us, that we can actually go through and we see, you know, that each value there, or each symbol rather, has a value. So whenever I look at this, I think that isn't saying, of course we see 2m, so saying 1,000 plus 1,000, isn't that just the same thing as saying 1,000 times 2?
Yeah.
I think so. So I definitely think that it would be easier to do multiplication if you're comfortable doing multiplication. So we have 1,000 times 2. Looking at our next value, C, Roman numeral, it would be 100. So we would do 100 times 1. Anything times 1, of course, is just 100. So we don't even have to write out, you know, each multiplication problem. If we can do it in our head, then we absolutely should. So I would just say plus 100. And then our next value there would be x. So we see x and we have 1, 2, 3. So let's see, x was 10, so 30. And then V would be our next Roman numeral, and we only have 1, so again, we could just add 5. And then the Roman numeral I, which doesn't mean your eyeball, Hope. I know you were thinking it. It just means the letter I is 1, so we have 2 of those, so plus 2. So we would just add those together, and then that would give us our solution to those symbols.
Okay, thank you, Katie.
But
That's
I
very
wonder,
well.
why do we even need to know this? Why do we need to learn it, Kim?
Because it has a very long historical background on how we have developed new ways to communicate with mathematics over time. So this is the Babylonian method. It's fairly simple and one of the most basic mathematics in time. So obviously we have the little, I don't know how to explain it. So we have 10 times 4 because we have 4 of them, and they're all equaling 10, which equals 40. And then we have simply just the 1. So our answer would be 41. Again, that plays a big historical background using mathematics. So now that we know how to do the Fabulous method, what base systems did the Mayans use, and how can we convert it into Indo-Arabic? I wonder if Hope can tell us that.
Well, this is going to be a little bit more complex because the Mayans use a very complex system. They actually use 2 systems, but they use a base 20. As you can see, all these little symbols and all these pictures, we see it's a base 20. So, and we see that they have 4 little symbols over here. So we see that there are 4 place values. So we're going to start at the top, and well, actually they work their way from the bottom to the top. So whenever you're doing the place values, you're going to start over here since it's using base 20, and this is 20 to the 0 power. This would be 20 to the first power, 20 to the second power, and 20 to the third power. So this is going to be 1, and this would be 20s, and 20 times 20 is 400, and 20 times 20 times 20 is, what is that, guys? 7,200, is that correct?
20 to the third power is 8,000.
8,000?
Oh.
Yes.
Well, I thought in the book it said that they used 72.
I just pulled out a calculator real quick. That way we
Yeah,
can.
but I thought in the book it said
Should I get the
72,000.
book?
Yeah, please, really quick if you can. But I'm going to go ahead and work right through these symbols. So our first symbol is going to be 17 is going to be this number here. So we're going to say 17 times 1 because that's our first place value. And then we're going to add that together with 3 times 20 because we have 3 20s. And then we're going to add this together with 6. And I thought that had a different number there too, even though we're using base 20. I'm pretty sure the book said something like 300 or something. Katie, were you able to find that?
I am still looking for that.
I know. I probably should have refreshed my memory before I
No worries. Hey, we are all human here, aren't we?
Guess so. Some days. Okay.
Mostly.
Yeah, mostly.
Well, hey, if you want to move on to the next question, we can while I look for this.
Okay, yeah, that's a great idea. Okay, well, now that we're trying to figure out how to multiply all these big numbers, it's actually probably the best way to move on. So, Kimberly, what is an easier way to multiply these large numbers?
An easier way is by using the lattice method.
Okay.
It's a method that we recently learned, and we're going to start by putting 28 at the top of the 2 boxes, which we have 2 boxes for a reason, and we have half of boxes for a reason as well. And I'll explain that here in a second. And we're going to put 32 on the sides. Okay, and we're going to start off. I'm going to start off by we're going to do 2 times 3, which is only 6. So we're going to put 0 in the first half of the left side box and put 6 in the second half. And we're going to do 8 times 3, which is 24. So 2 will go on top, and then 4 will go on the bottom. And then, sorry, just went blank again. And then we're going to do the same thing to the bottom half. Thank you, Hope.
You're welcome.
And then we're going to add diagonal. And so we'll just have 6 on the bottom row. We'll have 9 on the top row. Yeah, on the second row. Second row, we'll have 8, and then the first row will just be left alone for 0. So we'll have 8 plus 9 plus 6 will equal 23. So 23, sorry, I just went blank. It'll be 8,906.
Thank you, Kimberly.
How do I know?
It is a bit. of a long-lasting method.
Yeah, it is. How do I know if the diagram is set up appropriately, Katie?
Well, it's funny that you should ask that. You know, I noticed within your question that you had, it was 28 times 32, that it has 2 digits in each. So I see here that I actually have 3 digits in each. So it looks to me like you would just add a box appropriately for, you know, however many digits you have. So for this one, for instance, 3 times 3. You know, if I had 10 numbers, 10 digits, and my second number, then I would just add 10 boxes down, and so on and so forth. But that one we might just want to throw in the calculator, because that would take an awfully long time, wouldn't it?
It was long enough doing my question.
Absolutely. Yeah, so helping Miss Hope out here with our next box, we're going to have a 4 in the first triangle and a 2 in the second. And then 18 would be our second, or our third rather, number there. Going down to the next one, we have 0, 4, 14, and then 6. And then just jumping down to the right next one, 16, 56, and then 24. Miss Hope, I think you've been practicing.
Maybe this whole time.
I think so. And then Miss Hope's got it right. All we're going to do is just add those diagonals. Now, remembering we have to start with the most right-hand corner. And the way that I remembered that, you know how we're supposed to read from left to right? I think to myself, isn't it so silly, this lattice multiplication? We have to start from right to left. It's so backwards, isn't it?
It's almost
so 4. And then 14. Now remember, Miss Hope, you have to carry that one to the top there, that next diagonal.
Why is that, I wonder?
Well, because it's 2 digits. So it would just go to the next column. Just the same as whenever we're adding. If we were just to set this up, you know, like a regular, you know, addition table, then we would just carry that one.
So, and then we add these together, so it would be 9 and 18. 24. So we would carry a 2 this time?
Yes, we would.
So 3, 5, 6, 10, and 11. Because we're going to carry a 1.
Yes, ma'am.
7 and 1. So our total for this one is going to be
Yes, ma'am. You have it absolutely right.
all right.
So, hey, Chris, what have I done wrong if I end up getting the incorrect number when I use lattice? And what is maybe a way that I could check myself?
Well, it's actually quite simple. So going through the entire lattice method, you can see what the steps are incredibly simple. You're multiplying each number by their respective ones. So we would begin with how you're drawing. We have 9 times 5, then 6 times 5, then 4 times 5, and so on and so forth. Now, if you get an incorrect number, all you have to do is a form of checks and balances. Simply check your multiplication, and once all of those numbers are confirmed correct, all you have to do is check your addition, going through the different rows, and make sure that you've carried the correct numbers and that you've added them all together while also carrying more numbers until you reach the final row and add your final numbers together.
I made a mistake on purpose.
I see that, Miss Hope.
This is actually supposed to be a 12. Tricked ya. Okay, so now that we checked this, we checked our multiplication. How do we know how to add the squares correctly? Let's go ahead and do another multiplication problem and see that we have 4 digits and 3 digits on one side. So I'm going to go ahead and go through this one again. And you guys go ahead and help me with the multiplication table if you don't mind, because this is
absolutely
quite a few numbers. So we're going to go through.
So we have 8 there, and then 9 times 2 would be 18, 10, 4, and then going down to our next one there, we have 16, 36, 20, and then 8, And then the next one, we have 12, 27, 15, and 6.
All right, thank you. So whenever we're
Absolutely.
adding our squares, like you were saying, we have to start on the bottom. We have to work diagonally. And that's another thing, Chris, to answer your question too. Another mistake that we might make, because I know I did it whenever I first started this, is I tried to add the columns and rows up and down instead of going diagonally. And so that actually made quite a bit of a problem for me. So we're gonna go, like you were saying before, we're
13.
gonna go diagonally. We're gonna go through here and carry all these.
13.
Oh, I was thinking something else. Okay, and then again 13 again. Is that right? 20,
Mhm.
12, and then we're gonna carry our 1 here. And
Mhm.
then that is a lot of numbers. So a good way to do this would be estimating. So how would I go ahead and estimate a more complex math problem, Kimberly?
We'll do that by estimating to the nearest 10th or 100th or whatever makes the problem easier to round to.
Okay, so like let's look at this one. How would we go about estimating this?
So we'll do 883 plus 456, and we'll divide that by 134, and we'll get, sorry, I just went blank. Can we come back to this problem, Hope?
Oh,
Or can
I
you?
think I can help you out.
yeah,
Yeah,
no,
help me out. I just forgot.
Oh, no problem.
yeah.
Okay, so whenever we are rounding to the leftmost digit, what we're going to do is we know that whenever we round, if it's 5 and up, then we're going to round up. And if it's 4 and below, then we're going to round down. So I would definitely say for 883, I would definitely round up to 888. And then I would leave 465 just as it is. So I would say 888 plus 465 all over 134. And then I would say that also equals, now that I'm looking at it, I would say equals, now that I have 888, I would definitely round up to 900. 900 plus, I would say that 465, I could round up to 500. And then I would definitely put that all over, because 134, that's below that 5 mark. I would say over 100. So that equals 1,400 over 100, which equals about 14.
Well, thank you so much for helping me out with that. I really appreciate it.
Can somebody actually calculate like what that would, the total would be? So
Sure.
we actually added 883.
883 plus
Yeah. Let's go ahead and make
465.
this actual total. Let's do it.
Okay.
83 plus 465. What is that total?
1,348.
Okay. And then let's divide that by 134.
Well, it would give me a decimal, so it would say 10.059.
Okay. So 14 is kind of close to 10. I think that's a pretty good estimation. So would rounding to the right follow the same method as rounding to the left, Chris? Can you show us with this problem?
I certainly can. So before we do anything else, we have to make the denominator numbers, which are the numbers below the fraction line, let's call it, we have to make that simpler. So what we'll do is simply add 35 and 7 together, which will give us 42, I believe. And so once we have our denominator number, we're going to continue on as we did before. So rounding to the left number with 254, we're going to see that the middle number 5 is in fact 5 or higher. And so that's going to turn the 2 into a 3 and every number following is going to turn into a 0, leaving us with 300. Following that same method, we're going to attack 523. The middle number is not 5 or higher, and so the 5 will remain as is, and every number afterwards turns to a 0, giving us 500. And now we will attack the entire expression, 5 times 300 plus 500 over 42, which will give us our final answer of, I believe it is, tell me, Miss Hope. I did not have access to a calculator at this time.
2,000 over 47, right?
Over 40.
42, excuse me.
Sorry, I write my twos different. Okay, so what is that going to equal if we divide that out? Or would it be easier to say, to estimate 2,000 divided by 40?
I think it definitely would be.
It would be easier to do that for sure, because then you'd get a whole number, 50, instead of a decimal.
Yeah. So 50 is going to be our answer here?
Yes.
Okay, now let's go ahead and actually calculate that. Can somebody do 5 times 254?
254.
And then add 523 to that?
That's 1,793.
Mm-hmm.
Okay, and then we're going to divide that by 42. What does that give us?
That also gives us a decimal, and it would be 42.69.
42.69. See, that's pretty close. 50
Mm-hmm.
times 69. Okay.
I'd say that's a good estimate.
So whenever we're saying about, like, what does that wavy equal sign mean? Katie, could you show us with this problem?
Sure. Yeah,
So we're going to
sure
find,
can.
we're going to estimate, we're going to see what it's.
So that wavy sign, the solution to this equation is about 800. So those wavy signs means that it's about the number. It's an estimate.
So it's basically like an approximation.
Absolutely.
Just
And the
guessing.
answer to this one's 800.
Okay.
So we're going to say about 800, 800 divided by 300. Is that what we're going with? Oh, wait, isn't this a multiplication?
Yeah, I skipped the steps in between, but we can work it out if you'd like.
Oh, I see your total. Oh, I understand now. So we're saying that our estimation is about 800.
Yes, ma'am.
Okay, I'm sorry, I misunderstood. Okay,
Oh, that's
so
okay.
whenever we calculate it, let's go ahead and calculate it exactly.
Okay.
So
Sure.
you guys want to use our lattice method that we didn't learn before?
Sure.
I don't see why not.
Yeah. Let's
I
go
think
ahead.
we're going to need a bigger box.
Let's
I know. Hey, don't knock my boxes, y'all.
Okay.
Get your own box maker. Okay, here we go. 620 times 430. You guys want to help me out here? Let's go 24, 8. Wait, this is going to be 0, right?
0.
Here we go, 0.
Yes, it is.
Tricking us. Okay.
Tricky math people.
6. Oh, this is all going to be
0. That whole row will be zeros.
Safe to say.
Oh, what a
They got us.
boom.
0,
Okay.
0,
0.
8.
Oh, wait. 8.
That one's 8.
All right. And then this
Is that a 6 there?
Oh, that is a 6.
This is a 6.
14.
This is going to be also a 6, and then this is going to be a 2. So our answer is going to be 266,800 divided by 293. Anybody? Because I don't know how to do it with
Okay,
my
so
head right
266,800 divided by 293. 93.
Yes,
Yes.
ma'am.
Okay, that
correct.
gave us a decimal of 910.58.
That's what I got too.
Okay.
Pretty close, guys. I like this. All right, so why don't I just use a calculator? So we have been using calculators for all this, but the reason that we're going to do all these estimations for all these different problems is whenever we don't have the information, like with a calculator, it helps our brains to be able to think like, okay, let me look at this. 883, that's about 900, and we're going to add about 500. and 134 is about 100. And so it's better to like be a little bit higher than it would be to be under or all those things. Yeah, or just to get as close as you can. So it'd be about 14 would be our guess here. And then whenever we check later, it'd be like, oh, it's only 10. Okay, that's great. And the same thing goes with here. Like whenever we see all these this big thing of numbers, we're like, I can never do this in my head. But whenever you see and you make these numbers more whole numbers, it becomes a lot easier than
getting a bunch of decimals and
than getting a bunch of decimals and trying to calculate all that in your head. So it just makes us better at math, where we can recognize patterns better when we learn to estimate. And that makes us better at math overall. But yeah, we do carry around calculators in our pockets, so that's always good. And
it's all about making the numbers more digestible, all about making them easier to understand. And plus, we may not always have access to calculators on hand.
That's true. And like we're used to using, you know, all these numbers, and we've been adding all these together, and we've been talking about base systems. So Kimberly, what base system do we normally use?
Okay, so the typical base system we use is base 10, which is also known as like the decimal system. It's the most common base used today. It goes from the digits 0 to 9, and then it'll carry over after 9. So after 9, it would carry over, and it's the way we place value to a number. So we use base 10. There's also other bases that we use, and I think that Katie could help us out by explaining what other bases do we use.
Sure, I would love to help explain.
Different base systems.
So we have different bases. We could really have any number of base. We could definitely take a look at base 5.
Okay.
So like Kim was saying, you know, we typically use a base of 10. So we are very familiar with that, and we know that we're just counting to 10 over and over and over again. So what's going to be different is we're not going to count to 10. We're actually going to count to 5.
Okay.
So we would use the numbers 0 through 4?
Yes, ma'am. If it's 5 or over, then we have to carry.
Okay, cool. So this would represent like a 1's place, a 5's place, a 25's place.
Yes, ma'am.
A 125's, and what's 5 to the 4? 6. What is
625.
it? 625. Okay, and then whenever we're doing base 6, Katie, is it just the same thing, and we just use a 6 instead of a 5?
Yes, ma'am. All we would do is use a 6. So like you showed us, you did the 0 to 4. You could absolutely put a 0 to 5.
Cool. Okay, so let's try one out. Whoa, that kind of brought everything up. Okay, let's go ahead and try to add together a base 5. So let's go ahead and write 432 base 5 plus 133 base 5. So, like, we're going to say, since 2 plus 3 is 5, we're going to start all over with 0, and we're going to carry this 1 here.
Absolutely.
So we have 3 plus 3 is 6, plus 1 is 7. Well, we have 1 5 there, so we're going to carry that over, and that leaves us with a 2 here. So then we have 5 and 6. Well, that leaves us with 1 5 and 1 here. So our answer is 1,120 base 5. And then whenever we're doing base 6, we're going to add together. Okay, so you guys, Chris, could you help me out with this one?
I certainly can. So it's going to follow the same similar method as we used in base 5. So first we're going to add the first numbers together. So in this case, it's going to be the 5. We're going to bring the next number over the 2 and 7. And following the same method, we're going to add the 2 and 7 as well as the 1 up top. Bring over the number once more. We're going to add the 1 and 6. Bring those down, and we'll have our next coming numbers.
Cool. All right. So how do I find the place value in different base systems?
It's actually quite simple, just as you displayed. Each base system is going to, in a way, multiply by itself. So when you consider our base 10 system, it goes from 1 to 9, and then we have our 10, and then it continues to go upwards. But also a way to explain it is, so when thinking of base 10, we have our ones place, our tens place, our hundreds, our thousands, and so on and so forth. That applies to the other base systems as well. So when base 5, you're going to have your ones place, you're going to have your fives place, because 1 times 5 is 5.
Mm-hmm.
And next place, you're going to do 5 times 5, which gives you your 25th place. And when talking about base 6 notation, the exact same way, only instead of the multiples of 5, it's the multiples of 6. So 1, 6, 36, so on and so forth. And that will apply to all base systems. It's pretty interesting.
Okay. So so how do I borrow or exchange values in base 5? That's a pretty popular question that we've been encountering. So let's go ahead and write it out like we would normally write out a subtraction problem here. Okay, base 5. And now, it's really hard to think about borrowing in a system we're not used to. So what I like to do is called the chip method. And I'm going to draw out little chips for all my ones. And I see that I've got, in this larger number, I've got 4 ones. So I'm going to draw 4 ones. I've got 1 5, and I've got 4 25s. Okay. So I can take away 3 from 4. So that's going to leave me with 1. But I can't take away 4 from 1. So I'm going to have to borrow from my 25s. But there are 5 5s in 25. So I'm going to write it like this. And I can definitely take away 4 from here. And that's going to leave me with 2. But I see that I have, instead of 4 25s, I have 3. So my answer is going to be 321 base 5. Let's go ahead and try another, using the chip method, let's do another base 5 subtraction. So we're going to take 503 to base 5 minus 24 base 5. And we're going to draw out our chips again. We've got 5 25s. We have 0 5s. And we have 3 1s. Okay. Well, since we have no 5s to borrow from, we're going to have to borrow 1 25. And again, that's going to give us 5 5s. And then now we have one of these to borrow from. So we're going to add our 5 1s over here. Okay. And now we can start subtracting. So instead of here, we're going to have this as 4. We're going to have this as 4. And then this number right here is actually going to be 8. So 8 minus 4 is 4. 4 minus 2 is 2. And 4 minus 0 is 4 base 5. So you guys, we've learned a lot about number systems and computations. And we've learned a lot about ways to communicate with math. So I think we should be proud of ourselves. You guys have anything to add to that?
You know, I don't think so. I think we've absolutely done a wonderful job working together. Go Nerd Herd.
Yes, go Nerd Herd. All right, until next time, guys.
We'll see you. Bye.